Alright, now that you've understood basic string operations, let's move one step ahead by solving some intermediate problems. Problem 1. Check if two strings are anagrams. We say two strings are anagrams if they contain the exact same characters with the same frequency, but maybe in different order. For example, listen and silent are anagrams. Both have one L, one I, one S, one T, one E, one N. Intuition. First, check if the lengths of the two strings are equal. Then, build a frequency map for each string, and finally compare the two maps to determine if they are the same. Pseudocode. Function is anagram, S1, S2. If length of S1 is not equal to length of S2, return false. Create empty map frequency 1. Create empty map frequency 2. For each character C in S1, increase frequency 1C by 1. For each character C in S2, increase frequency 2C by 1. If frequency 1 is equal to frequency 2, return true. Else, return false. Dry run. Example. S1 equals listen, S2 equals silent. Step 1. Length check. Length of S1 equals 6. Length of S2 equals 6. Same length, continue. Step 2. Build frequency map for S1. Start with empty map frequency 1 equals empty map. Traverse S1 character by character. L, frequency 1 equals L1. I, frequency 1 equals I1. S, frequency 1 equals S1. T, frequency 1 equals T1. E, frequency 1 equals E1. N, frequency 1 equals N1. Step 3. Build frequency map for S2. Traverse S2 character by character. S, frequency 2 equals S1. I, frequency 2 equals I1. L, frequency 2 equals L1. E, frequency 2 equals E1. N, frequency 2 equals N1. T, frequency 2 equals T1. Step 4. Compare maps. Frequency 1 and frequency 2 both contain the same keys and values, so return true. Time complexity. Building frequency 1, O of n. Building frequency 2, O of n. Comparing maps. If characters are limited, like lowercase English letters O of 1. Else, O of k where k is number of unique characters. Total, O of n. Space complexity. Two maps holding up to 26 lowercase characters. O of 1. In general case, O of k where k is number of unique characters. Problem 2. Longest common prefix from array of strings. Intuition. We are given a list of strings, and we need to find the longest starting substring, prefix, that is common to all strings. Example. Input, flower, flow, flight. Output, FL. Idea. Start with assuming the first string as the prefix. Compare the prefix with each next string. Shrink the prefix from the end until it matches. Return the remaining prefix after all comparisons. Pseudocode, language independent. Function longest common prefix, strings. If strings is empty, return empty string. Set prefix equals strings 0. For I from 1 to length of strings minus 1. While current string does not start with prefix. Remove the last character from prefix. If prefix becomes empty, return empty string. Return prefix. Dry run. Example. Flower, flow, flight. Start, prefix equals flower. Compare with flow. Does flow start with flower? No. Shorten prefix to flow, still no. Shorten to flow, yes. Keep prefix equals flow. Compare with flight. Does flight start with flow? No. Try flow, no. Try FL, yes. Keep prefix equals FL. No more strings left. Final prefix equals FL. Time complexity. Let n equals number of strings. M equals length of the shortest string. In worst case, we compare m characters with each of n-1 strings. So total comparisons equals O of n times m. Space complexity. We just use a prefix variable, no extra space used, excluding output. So space equals O of 1. Conclusion. Now that you've learned these intermediate string problems, You've taken a big step from basic manipulations to solving real-world coding problems that involve mapping, comparison, and pattern matching. Keep practicing, and soon you'll be ready for more advanced string algorithms like sliding windows, KMP, or Z algorithm.